and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad you've taken the time to join us today, and I hope you find something useful out of the presentation as we look at our topic of 4 methods to reduce scrap and rework in your manufacturing process. Now, just to keep in mind, if you do have any questions, feel free to go ahead and pop those into the chat, and we'll look at those after the demo portion of today's presentation. And so with that, our topic is scrap, and scrap does happen. And there are different levels of scrap. So if we take a look at basically 3 different types of categories, we have rejected raw material that comes to the facility that may not be up to standard, and so that may be a portion of scrap. Another scrap definition would be items that have been partially processed. This would be things that happen during maybe movement through the facility that get damaged, or in the case that we're talking about today, it could be fastening errors that would lead to rework that needs to be done, but it's a partial process of the item or assembly. And then lastly is going to be a failure to meet the specifications as the final product is built. And so these are 3 different areas of scrap. We obviously are going to be focusing on the fastening portion and how we can help to reduce that through the use of some advanced technical terms or tools that we have available for us. And so that leads us kind of to some of the advances that we've seen in manufacturing here recently. And it's going to give us the ability to execute production tasks at a much greater level of visibility during the entire process. And that includes smart-based equipment such as DC type control tools, where we do have a lot of control of what happens during the actual fastening process. And we'll talk a little bit more about that as we go through the presentation. This also gives us the ability to be very flexible with automating different materials on different parts of the application, because of the fact that we do have the ability to take advantage of some of the smart tools that are currently available. And this also does give us good visibility on being able to process the actual monitoring of the data that is happening during the actual assembly build. So a lot of Industry 4.0 type of information that comes with that type or this type of tooling that does allow you to be able to get that information almost instantly and be able to look at that and parse it through the use of data acquisition through the different means of communication with different types of smart tools. Lastly, we're going to be looking at the error proofing technology that comes with this type of tool. And this is where we can really help to reduce those scrap rates, is by error proofing the assembly so it does not have the opportunity to, or we give the operator the opportunity not to make a mistake through the process. And if there is an error or a mistake, it's immediately found or immediately corrected at that point. So those are some of the advances that we've seen here recently with that. And so when we look at causes for defects in the assembly process, the number one most often defect is going to be happened and done by the operator or a human influence into the actual defect that takes place. And so if we can, again, as we talked about, and we will talk more about the error proofing aspect of the assembly. If we can control what the operator can and can't do, then we can help to minimize the different defects that we might see within an assembly operation. There's also going to be obviously common tightening failures that we would see during the process. So you may have errors where the fasteners may be missed, fasteners may be under torqued, fasteners may be over torqued, or in the case of working with a power tool, you may have the operator let go of the tool before it actually completes the cycle, and so you're going to have a lifted fastener. All of these types of things can lead to failures, especially if we have an under torque situation. Any type of vibration is going to cause that fastener to possibly back out and then fail. If we have an over torque type of situation, that fastener may be stretched to its yield point, and any type of vibration of that is going to cause that fastener to then fail and break. And so if we can again get to a point where we're having the correct torque being applied at the correct fastening location, then we can help to again minimize the actual scrap that is being developed, or at least minimize the amount of rework that would need to be done in a specific assembly process. So that's going to lead us to our poll question for today. We'll go ahead and launch that poll, but we're going to be asking basically your current rate of scrap that you may see within your process. And so is it going to be less than 1%, 1 to 2%, 3 to 5, or over 5%? So we'll give you a second here to go ahead and answer that, and then we'll move on with the presentation. All right, thank you for participating in the poll. We have some last minute here entries, so we'll go ahead and stop that. And it looks like the majority is in the 1 to 2% camp, followed by 3 to 5, and then less than 1, and a few that are over 5. So thank you very much for participating in that poll. And as we look at the 4 methods to go ahead and reduce your scrap rate, the first one, we just touched on it here, is going to be the error proofing process. So again, if we can help to shape the operator's process and giving them the ability not to make a mistake, you may be familiar with the Toyota manufacturing method of only giving the operator the opportunity to do the correct thing. And this goes along with a lot of error proofing things that we see in everyday life. You know, if we're using a grounded outlet plug, it's going to be bigger on one side than it is on the other. And the outlet will only allow us to plug it in with the correct orientation. We see it when we go to get gasoline at the gas pumps. You know, we need to make sure that the nozzle is completely in there before it will allow us to go ahead and fill that. And once it does get filled, it releases that. These are the type of error proofing processes that we're talking about. In the fastening process, if we can go ahead and we can detect if there's an error or it happens right away, we can go ahead and identify that and correct it at that particular moment. This helps also to make sure that we have the correct torque that's being applied that we're looking for a specific fastener or fastening location, as we'll look at within our demo process. But you want to make sure that you're able to detect any type of fastening error that may present itself. If you see errors that may be consisting of cross thread type of issues where the cross thread is going to happen right at the very beginning of the rundown. That fastener will bind up. The tool will certainly reach the torque value, but because it did not have enough turn to fully seat itself, we can monitor that type of process, and we can set that a particular fastening location must meet a certain amount of turn or angle for that to be considered a good rundown. We can also detect fastening errors such as a stripped fastener by looking at what is going to be the maximum amount of turn that we would allow for a specific fastening location. And if it goes past that, then that would present an error to us as well. Or if the item actually goes outside of a torque percentage limit for that particular location. So we can detect those fastening errors. And again, we have the opportunity to correct it right when it happens. And that kind of leads us to our second method, and that's going to be process control. If we can then have our error proofing process in place, and we can then build a process control around that, where we can actually build a programmable assembly sequence within the use of the Smart tool. Because we have the ability to use different presets with different torque values and different characteristics for that particular preset, we can then utilize that for the assembly process, where we can monitor where the tool is and change the torque for that automatically within that sequence process to make sure that we get a good, efficient assembly process, excuse me, that we can then again monitor tolerances for torque at each of those fastening locations. Each of those different presets can have, again, their own unique programming to deal with the different angle requirements, the different torque requirements, maybe different RPM requirements that we might need within that. But all of that can happen as the operator moves through the assembly without them having to do anything to change a preset or use a different tool. It could all happen all at the same time. Again, allowing us to have multiple fastening tasks within our process control. And again, this can help to minimize workstations as well. So if you've got a number of workstations that may only have one or two tools at them at different torque values, because the Smart tools do allow us to have multiple different presets, we maybe have the opportunity to consolidate those during that process with that process control. Next is going to be the use of a transducerized tool within the Smart tool. And basically that just means that we have the ability to measure the torque that's being generated by the tool itself. So it has a built-in sensor to it. It is also then communicating the torque results to the system itself, whether that be stored locally on the controller or if it is sent to an MES system through the use of some of the protocols that we have available and the different I/O configurations. But if we do have that ability to monitor what's happening with the torque, again, if there is an issue, we can correct it right away. And that leads us to our third method, and that is going to be the ability to have a data acquisition type of collection system. This then gives us the ability to record and store the torque data, and this really gives us the ability to have a data-driven decision making, where we can also look at different characteristics that may happen during the fastening process. We can then respond to those issues that may come up. We can also use these to compare different types of patterns or different processes or it could be the ability to look at, excuse me, different shifts that may be using or having issues. You have that ability to look at the data and make a constructive type of decision around what may be happening with that to help, again, optimize and improve the productivity of your assembly process. And then the last item in our method is going to be the fastening automation process. And so this automation process, again, goes a little bit hand in hand with the process control, because if there are things that we can change and that we can control automatically, this can, again, help the operator just to move through their particular application and not having to think about changing any presets or changing anything else as it relates to using the tool. Then that certainly can help in the automating of that process. This also goes for using items such as a bit socket tray selector. So if the operator pulls or needs to use a different bit, that communicates to the smart tool and automatically changes the preset that would be used for that particular bit. It could also be automating how fasteners are delivered. Do you want to use a screw presenter to allow the operator to simply grab that fastener and then go ahead and move through their process? Those automation types of processes, again, can help in reducing the amount of decisions that the operator has to make. And the less that we can do that, the less scrap that we can be generating. And so, excuse me, I need to get a drink of water. So as we touched on, using the automation processes as things that we can replace that manually we would be considering using in the assembly process. And the last would be the use of the digital IOs or the interface with that. And this, again, goes a little bit with the process control, because we do have that ability to communicate with a PLC or communicate with an MES system where we can have information sent to the controller. So if you have basically maybe a high mix, low maybe type of build scenario where the PLC can send information directly to the computer, to the controller, update presets, change presets, because of the ability of the smart tool to have a read-write address that it can communicate with the PLC over different protocols, those types of things. If we can utilize those digital interfaces, again, to help us be as efficient as possible, as well as being accurate as well, in being able to take a look at the error proofing aspect of the actual assembly. So that is going to be the 4 different items within the process. So if we can error proof the assembly, implement process controls with that, be able to capture and analyze the data from the fastening applications, and then also try and automate certain things within that. Again, that can help us control what is happening with the assembly to eventually reduce our scrap rates. And again, scrap is not only time or product that may need to be absorbed, but it is, if there is rework, we have that type of cost and burden with the actual rework of the time, storage, and again, the product that we're being used. So let's go ahead and we can jump into our demo portion of the presentation. And with this, I'll be showing our DC Smart tool, which is our ECTD controller, which is our transducerized DC tool. And it will also be used in conjunction with our DPC touch position torque arm. And so what's really nice about this system is that we can help to visually move the operator through the assembly process. And for each location, we can call for a specific preset, and we have controls around that based off of how we program the controller. So let's go ahead and do that. So in this scenario here, I have a thread block that we'll be dealing with. We'll just use these 3 fasteners up front here as our application. And then we have our controller, and then we have the DPC touch. And so with that, let's go ahead and jump into how this functions and the different ways that we can go ahead and do the different process controls that we might be looking at. And so right now, what you see on the screen is that our tool is actually locked. So there's no power to the tool here. So if I try to press the trigger, we're not getting anything from the tool itself. We have our different presets that we might be using here. This unit does have the ability to have 15 different presets, along with 2 specialized presets that we can use. That would be our multi-sequence process, but that's for another discussion. But then we have our DPC touch controller. And so this is where we can go ahead and we can create different assemblies to help move the operator through the process. So if I go to our job manager, you can have a number of different jobs in here, up to 250 or so different job configurations that we can use. So I'll go ahead and select the one that we're looking for today. And in this case, we can have an image of the actual part that we're working on. And then we have a target location of where we would be fastening. And so obviously I don't have an engine here on my desk, but nevertheless, I think you kind of get the point. And so how this works is once we move the tool into the right location, which is going to be this fastener here, it will then go ahead and allow the tool to have power, and it will go ahead and select the proper preset. Now, the way we have this particular program set up is that these 3 fasteners here will be a 2-pass type of an assembly. And we are just going to run the first pass down 500 degrees of rotation. So we're just turning that fastener 500 degrees. So 1 revolution is 360 degrees. So we're going to go a little bit less than 2. This can help to simulate a flange type application or something that needs to be seated very, very precisely, so we don't get part of the assembly that is higher or that may cause a leak or those types of scenarios. And so in our preset, we have that set to just run an angle. So we can have the system run to a specific torque value, or we can have it run to a specific angle. And so for preset 1, we have that set to run to a specific angle. So once I get to the right location, you can see that the indication here will change colors. It changes to a green color. And if we want to see how this is working, we do have 2 encoders that are monitoring the tool as it's being used or being manipulated. Once we get to the right location, both of those values must meet the saved value for it to go ahead and give us power to the tool. So if we go back to the image, We come to our first location. I can go ahead and run that. So our angle here, we ran it 499 degrees plus 2 in our additional angle. So we went 501 degrees of rotation. It has now indexed to fastener number 2, which is a different location. And once we get to that location, again, we now have power to the tool. You can see that we're in an okay state once I get to the location. If I go outside of it, it will go ahead and lock up the tool. So if we run this one again, now we've indexed to our third fastening location, and we can run our preset 1 again, which is 500 degrees of rotation. Now we're doing our second pass. This will go ahead and fully seat the fastener. It is now going to use preset 6 for the first fastener. It'll use preset 5 for the second and preset 7 for the last one. Now, if I go ahead and run this, we do have our target torque that we are going to achieve. So our target torque was 2.5 Newton meters. We ran it to 2.53 Newton meters. It is now indexed to our second location, and you can see that our size on our target is a little bit different than the first target with the first sequence. That's just to show you that you can change the size of that if needed. We can go ahead and run this one, and now we move to our final preset. Now this is preset 7, and the way we have this set is to monitor the amount of turn that would happen if we were to see a stripped type of fastener. So I deliberately have this set a little bit higher than the other two. So as we run this one, once we reach an amount of turn of over 850 degrees, the system will go ahead and generate an error. So we had our angle that was over that. The system did not count that as a good fastening. So now we have the opportunity to go ahead and re-attempt that. If we so desire, we can set this to have up to 9 attempts at one fastener before it would reject the part or this job altogether. So if we come back to the image, you can see we're still here. We still have 2 of 3. Once we get to this location, we can go ahead and we get a good signal. It then will go ahead and repeat that. If we are using the same part, we could also lock up the system, make the operator or have a PLC again, or another device select the program that needs to be used. But in any case, we have the ability to error-proof this assembly process, so the operator doesn't have the ability to make a mistake. They can't go ahead and use the tool in the wrong location, because the tool will only have power in the right location. And depending on how we set up the program on our controller, the touch system is going to be looking for a good signal before it indexes to the next location. So that is the demo portion of today's presentation. And next we'll go ahead and we'll move on to any questions and hopefully answers that we can provide you. So Chris, do we have any questions?
Sorry, Dave, I was muted. Can you hear me,
No
Dave?
problem.
Okay. The question was, can we add a barcode scanner to the system that you just demonstrated?
We sure can. So we can use the barcode scanner with either portion of the system. We can use it on the Smart Tool, or we could use it with the DPC Touch to call up a specific program or job within that If we use it in connection with the Smart tool, that barcode can also be inserted into the data field. So if we would like to monitor a specific part as it moves through the process, we can monitor that as well. But a barcode scanner can be used with both cases to either initiate a specific job, pull up a specific job, and give us the ability to add that to the data stream.
All right, Dave. The next question we had is, how do you select the correct torque?
So if on our screen or the torque value is done through programming the actual unit. So if we log into our controller here, we can come into our parameter menu, go into the fastening. We have our different presets that we can use down here. So if I select, let's say preset 12, I can go ahead and enter that. I can simply select our fastening type, which is going to be, let's go ahead and zoom in just a smidge so you can see that a little bit better. So we have our different type of programming. So this is a torque control. We can enter in what our target torque is. And so if I tap on this here, I can go ahead and I can select, say, 5 Newton meters, enter that, and now it has updated that preset to whatever value we would like to add for that. So it makes it very easy to be able to update or change or do a preset that that you might want to use. Now this is fully behind the login. So the operator does not have the ability to be able to do this. And have to be done by an administrator. So,
all right, Dave. The next question: is there a redundant measuring or closed loop measuring in the tool to prevent calibration out of tolerance conditions?
Yeah. So in that same menu that we have there, we have a torque tolerance field where we can set a percentage. So if it sees the torque go outside of that, we would see an error outside of that tolerance. You can also put the tool itself on a torque analyzer, and you can calibrate the tool to that specific analyzer. We do also have the ability to adjust the torque output of a specific preset. So if we see some joint characteristics that are maybe present some challenges to the torque output, but we want to keep the torque value the same, but we need more power because of our testing, we're seeing that it may not be reaching that particular value. We can turn up or turn down the amount of output that happens for that particular preset. So there again are a lot of different fields and different ways that we can look at handling a specific joint characteristic and be able to try to set the tool up to manage that one as best it can.
All right, Dave. Next question we had was, does the Mountz equipment need to be calibrated by Mountz, or can it be calibrated by other companies, and how often?
So how often is going to be dependent on your own QMS systems that you may have internally. Anywhere from 6 months to a year would be a typical type of standard. These tools can be measured and calibrated by other calibration facilities or in-house calibration teams as well. So that is not exclusive to Mountz at all.
All right, Dave. The next question is, what's the difference between a non-transducerized tool and a transducerized tool? Sorry.
So there are basic The difference is that with a transducerized system, it has a built-in sensor that is monitoring the torque and being able to capture that value when the tool shuts off. A non-transducerized tool or a current type based tool will use the amount of current draw as its reference to the amount of torque that is being applied. Now, both can be extremely accurate with that. So the only difference is that one tool has a built-in measuring device and the other one doesn't.
Okay. And then the last question we have is, can the system be used for like a thread tapping application as well?
Yes, it certainly can. We do have some specialized modes that will allow us to actually go over the seated torque as a thread may be cutting, and then drop the tool back down to look for the final torque after the threading has been cut. We could also use the angle parameter to go ahead and cut through that thread to just turn that fastener. Once it's cut, then we can use what would be our multi-sequence process, where we can add another preset to a specific rundown. So one preset would cut the thread, the other preset would look for the final torque, and that can be incorporated all within one trigger pull event. So we certainly can use that for certain thread tapping applications, certainly.
All right, Dave. That was it.
All right. Thank you so much. Appreciate your time. Again, we hope you found this useful, and we look forward to seeing you in next month's webinar. Until then, have a great day, and we'll see you soon.